Okay, hello everybody to this week's ISGC seminar talk. This week's speaker is Donghan Yeom. He did his PhD in 2011 at KAIST and is now an assistant professor at Pusan National University in the Departments of Physics Education. And today he will talk to us about quantum black holes, what we can know before we solve it. Thank you very much, Donghan, for giving this talk. The stage is yours.
Thank you. Can you hear me? Can you hear
Yes,
me? No problem.
yes.
Okay. This is a very good opportunity, very great opportunity to provide my recent interest in front of this very intercontinental and worldwide seminar. My main position is in Pusan National University, which is located in South Korea. But now I'm in sabbatical year and I'm staying in Waterloo in Canada. Maybe you may estimate that my time is now 2 a.m. here. This is a very quiet time, and it's very good to provide. Good to focus on the research seminar. It's a very good opportunity anyway. Using this opportunity, today I hope to discuss the title is quantum black holes. And I made the subtitle "What We Can Know Before We Solve It," but I will explain the meaning of this subtitle later. Using this opportunity, I hope to introduce myself and also my research interest. And I'm happy to have any questions. So please, if you have any questions, then please interrupt in any time for any questions, and I'm very happy to that. Okay. I bring these two pictures. One is the famous ocean side of Busan, the Haeundae Beach, and some of you might visit here. But this place is very beautiful, but the price is very high. So usually, my house is quite far from this beach side, and this second picture is the university, Busan National University, and here is the mountainside. You can notice that it is the mountainside, and my house is also nearby this mountainside of the Busan. I came from Busan National University, and I'm in the Department of Physics Education. Probably you know about Busan. Which is oceanside city, and also it's quite famous of this movie. I think some of you know about this famous movie. I mean, Train to Busan, and so you should be very careful to ride the KTX train because some zombies may appear time to time. Yeah, I'm sorry, it's a joke, and Um, I couldn't see any of your face, so I'm not sure whether my joking is working or not. Anyway, okay, so using this opportunity, I would like to introduce my research interests and discuss my fundamental questions that I hope to think, especially I hope to think on, during my sabbatical year and for next several weeks. And some ideas are still ongoing, and I hope to introduce some of them. And if you have any good ideas or any interesting topics that we can collaborate, then I'm always happy to discuss and start any new collaborations. So for several years, one of my the most important research topic and my interest was about the black hole information paradox. Maybe you know quite well about uh, black hole information paradox. So black hole should evaporate and eventually disappear within a finite time, and you can ask whether the information will be preserved or not. And there might be several. Ways to think. This is summarized in my previous review paper, which was published in Physics Report in 2015. And in this paper, we mainly focused on the remnant picture, but this is not the only idea to understand the information loss paradox. So, for example, you can ask whether information conserved or not, and if you say no, then maybe there is information loss, but this may cause some disaster. If you believe that Hawking radiation carries information, then you go to the old paradigm, so-called the black hole complementarity, which was developed in 1993. However, several years later, some people found that the original version of the black hole complementarity has some inconsistency issues. So one of the approach is based on my paper, although it's not cited, highly cited. And later, more highly cited paper is the so-called AMPS paper. It's based on several arguments. My argument or AMPS argument, according to this argument, black hole complementarity in itself is inconsistent. So it was, I think that now it's widely accepted by the community. If Hawking radiation cannot carry information, then where is information? Maybe information is retained by another object. If the answer is yes, then you should think about black hole remnant. But the remnant can have a very wide notion, either bubble universe or baby universe or possible or any other interesting ideas might be inside here. However, in my frank opinion, probably the true answer must be in this question mark because this remnant idea is more or less very specific, so it can be realized only specific situations. Therefore, after this, my struggle to understand information loss paradox, probably the answer is somewhere over this question mark. So, yeah, so if I review my journey to the final answer to the information loss paradox, I criticized the original version of black hole complementarity. So if the original version of the black hole complementarity is wrong, then what's the alternative idea? So when the AMPS provide this inconsistency issue, their resolution was that to radically modify the general relativity around the horizon scale, that is so-called the firewall conjecture. So then you can ask whether there is really a firewall or not. And in this paper in 2000, no, no, okay, 2015, we reported that indeed that idea seems not consistent in the sense that if the black hole behave non-adiabatically, then some effect may make the firewall to be naked. This changes too many things, not only inside the black hole, but also outside the black hole. Yeah, so I wanted to criticize the firewall idea once again. But interestingly, nowadays, in the very recently, people know more to say about the firewall idea because they have a better idea to explain the information loss paradox. Then what is the better idea? And yeah, what can we learn from this debating? So from this debating, what I could understand is that the true resolution of the information loss paradox must use non-perturbative effects. So perturbative effects cannot explain the information loss paradox because it makes the inconsistency based on the black hole complementarity and other discussions. So there must be non-perturbative effects that probably comes from genuine quantum gravitational effects. I mentioned that nowadays nobody seriously think about the fire idea because um, quite many people think that there is a better idea to understand the information paradox based on non-perturbative effects. That is, some people will accept that the replica tricks and replica wormhole contributions is a kind of non-perturbative effect that explain the information loss paradox. I myself is quite doubtful whether the replica tricks will entirely resolve the information loss paradox or not. And during today's discussion, I will briefly mention what is somehow more conservative understanding about this question. But anyway, so what we can um, conclude, or at least what I myself could conclude is that non-perturbative effects are very important to understand and resolve the information loss paradox without further inconsistency. Uh, I will welcome any of your questions or any criticism and so on. Okay, so yeah, if you can accept that non-perturbative effects are very important to understand the information loss paradox, then the question is how can we compute non-perturbative effects of evaporating black holes? And somebody will say that it might be the replica wormholes, or some people will say it's somehow new another contributions. And how can we sure which approach is correct? Uh, and frankly speaking, we surely do not know the answer because we don't have the fundamental quantum gravity. However, it's possible that we can follow the most conservative approach. Um, what is the conservative approach? That is to follow the canonical quantization. You can see this paper. This paper was published in 1967 by Bryce-DeWitt. So this is a very old paper, but I think this is the most conservative approach toward the non-perturbative quantum gravity. That is so-called the canonical approach, canonical quantization. So canonical quantization means that you introduce some canonical variables, and also you can prepare some canonical momentum. The canonical momentum will be on operators, something like these operators. You can see that this looks like the derivation. And this is something like the momentum operators of the quantum mechanics. So in usual undergraduate level quantum mechanics, there is a momentum square term. So this is exactly p square term, and this is the potential term. And therefore, this means that the inside the parenthesis is that it's the Hamiltonian constraint, and the Hamiltonian times psi equals zero. Uh, that means it's a kind of Schrödinger equation. So what is the canonical approach? And the answer is we introduce the Schrödinger-like equation and solve it. And then, of course, this will include every quantum effects in principle, not only perturbative, but also non-perturbative effects. So probably this canonical approach is the most conservative approach to include the every perturbative and non-perturbative effects. Uh, I'm saying this by several words, and I mean several sentences, but practically it's not really so easy. So yeah, basically we have two kinds of equations. So one is the Hamiltonian constraint, and its a quantum version is the quantum Hamiltonian constraint, so-called the Wheeler-DeWitt equation. This is the Wheeler-DeWitt equation. And also we have momentum constraints, which should be satisfied in the quantum version. So quantum momentum constraint. So in low quantum gravity community, this quantum momentum constraint is quite important, and this will provide the loop representation and so on. But in my talk, I will practically approximate this is satisfied, and I will only focus on the Wheeler-DeWitt equation, because the Wheeler-DeWitt equation should carry the information about the time evolution, although there is no explicit time, but this should have some information about the time evolution in some way. So, okay, so I will introduce the generic procedure and generic recipe to do the quantum gravity in canonical way. It's very simple and very easy, so probably you can follow according to this recipe. So the first step is to write down your Lagrangian. So this Lagrangian means you can think any classical Lagrangian from the beginning. Okay, so you write your Lagrangian. The step two is you convert the Lagrangian to Hamiltonian using the Legendre transformation. So, yeah, you already know this process in second grade of, I mean, classical mechanics course in undergraduate course. So it's easy. So you introduce canonical variables, and you introduce generalized momentum variables, and using this, you can introduce the Legendre transformation, and finally convert to Hamiltonian. In step three, so up to step one and step two, these are all the classical process. But in step three, you change the momentum to operators. So you change the momentum p to partial x, where x is the conjugate of the momentum. Okay, then if you change the momentum to operators, then you will obtain the Hamiltonian operator. Then you must multiply to h times wave function, and it becomes zero. So this is the quantum Schrödinger equation, or in the gravitational system, it's known as the Wheeler-DeWitt equation. So you will obtain the Wheeler-DeWitt equation. Then what is step four? Then you can solve it. So if you have an equation, then you can solve it. And then what should we do? We should compute some observational quantities, observables. So what is the observables? Sometimes it's quite complicated, but either it's eigenstate or eigenvalues or some expectation values. Um, and if you compute these observables, then if you compare these observables with the real experiments and experimental data, then and if they agree each other, then you will get the Nobel Prize in several days later. So it's very easy. So it is a very big framework to the canonical quantum gravity in general way. It's that easy. Yeah, but you may feel that I am joking to you. So still, I cannot see your face, and whether you understand my joking or not. But this process is totally very complicated. Uh, yeah. So the problem is this procedure. So we have a very big plan from Lagrangian to computation of observables. Um, so yeah, you can prepare such a plan, but the problem is this procedure is not that easy. So the question is why? What is the most difficult point to do such a process? This is a important question, I think. So, what's the problem? And Of course, there might be very many problems, but one of them is this kind of issue. For example, in my paper with Martin Boswell and Sudo Brahma in several years ago, we thought about the canonical quantization of Schwarzschild black holes. I mean, the black holes with spherical symmetric background. So in the spherical symmetric background, we must assume a kind of metric ansatz. So n is the left function, nx is the shift function, and so n and nx are the gauge variables, and more canonical variables are qx and q phi. So, so therefore, this Qx and Q phi must be decomposed by several canonical variables. But in loop quantum gravity community, they introduced the Ashitaka variables, so represented by E phi and Ex. So uh, for given Ex and E phi, there must be a corresponding canonical momentum, which is K phi and Kx. So by introducing canonical momentum and canonical variables, you can write down the Hamiltonian of this spherical symmetric system. So that means it's not impossible to write down the Wheeler-DeWitt equation for black holes. It's not impossible. You can do it. So this is not the unique way. If you choose another variables, then the shape might be changed. But if you choose the Ashitaka variables, then it should look like this. Uh, so it's okay to write down the Hamiltonian constraint, but the problem is that if you change it to k phi and kx as the differential operators, this equation is still very ill-defined. That's the problem. So the reason is that in the potential part, this and this part are the potential part, but in the potential part, there is EX prime contributions. So the prime is the derivation with respect to the spatial variable X. However, if the quantum Hamiltonian constraint is a kind of a partial differential equation, then the partial differential equation must be presented by kx, k phi, and ex, e phi explicitly. But interestingly, this potential part has the derivation of ex prime and e phi prime. Such a prime contributions exist. Therefore, this Hamiltonian constraint is not a partial differential equation, but kind of a functional differential equation. That's the problem. So if it's a kind of a partial differential equation, then there must be a way to solve it. Even though it's not possible to solve it analytically, you can solve it using your computers. However, if it's a functional differential equation, then we don't have a good way to solve it in a straightforward way. That's the problem. So it's somehow ill-defined, and that makes very difficult to solve it in a direct way. So even in the quantum gravity community, we cannot directly solve the Wheeler-DeWitt equation. So the usual strategy in the quantum gravity community is to modify the classical Hamiltonian that includes some quantum effects, comes from the momentum constraint. So the momentum constraint means we can introduce some loop quantum gravitation effect, and there is a reasonable, there is a good reason that such a loop effect modifies the momentum part this way. And then still this Hamiltonian can be regarded as the canonical Hamiltonian, but it was modified by this way. And if you regard this Hamiltonian as classical, but quantum modified classical Hamiltonian, then you can effectively describe some quantum gravitational effect. In my understanding, that is the best way to resolve the issue in the quantum gravity community. But still, it's not possible to directly solve the Wheeler-DeWitt equation because this equation is ill-defined. Okay, so I said why the canonical quantum gravity procedure is not very easy to success, but there is some remarks. So even though we cannot solve the equation for a stationary black hole directly, but thanks to constraints, for example, the energy conservation of a stationary black hole, then if we think about the energy conservation, then the equation will be determined by only asymptotic charges. So, for example, asymptotic mass charge and electric charge and angular momentum. These asymptotic charges will determine the wave function. This was proven by Kukachi in 1994 in this paper. So that means we don't know how to solve such a ill-defined functional differential equation, but for some extreme cases, for some stationary black hole cases, we don't have to solve it. That's the very important point. However, this is not very sufficient in the sense that indeed what we are interested in is the dynamical black holes. So in the dynamical black holes, somehow the asymptotic charges must be changed because the mass should change it and charge also change it and also angular momentum must be changed as time goes on. Such a benefit of Kukachi cannot be applied for a theory with matter fields that can induce Hawking radiation. So anyway, to implement such a non-perturbative effects, anyway, we must solve the Wheeler-DeWitt equation in more direct way. But it seems it's not very easy to perform such computations. It's difficulty. So the question is there any better way to do computations? Is there any better way to solve the Wheeler-Dewitt equation in a more direct way to compute the non-perturbative effects of black hole evaporation and so on? This is a very important question. So you may remember that the title of today my talk. So it's a quantum black holes and what we can know before we solve it. So that was my title. So my idea today is that the better way. What is the better way? Such a better way is not to solve the ill-defined equation, but before we solve it, there might be some indirect ways to catch some important physical essence. That is my strategy of today. But later, I hope to uh, solve such a problem in a more direct way. Uh, but yeah, today in my talk, I will focus on indirect way to bypass such a ill-definedness issues. Yes, then you can ask, how can you know before we solve it? And there is some idea. So there
Excuse me.
might be an
Can I ask
exceptional
a question?
cases.
Can I ask a
Yes,
question?
yes,
Yes. So,
yes.
so if we consider two-dimensional gravity, maybe we can compute some quantity. As you know, two-dimensional gravity is well defined, and the the issue of the Wheeler-DeWitt equation is only for higher dimension, or it's still problematic even in two-dimensional gravity.
That's a very good question, and also in two-dimensional case, there are many versions. But in my knowledge, for example, if you consider the CGHS black hole, that is dilaton-coupled
Yeah, yeah.
gravity, in two-dimensional case, then such a ill-definedness issue still appears. So in the
Uh,
Wheeler-Dewitt equation, there appears the potential term and some spatial derivation term appears there. But I'm not sure if you think another gravity, two-dimensional gravity model. If this make the Wheeler-DeWitt equation simpler, then I think it's very interesting. If you can find such an example.
I see. So what is this mean? So in two dimension, yeah, we can compute several quantity, but only so you mean the Wheeler-DeWitt equation is we should not use Wheeler-DeWitt equation, or in these some yeah, I don't know what we should do, but
Okay.
yeah,
Yeah,
okay,
definitely.
yeah, yeah. Of course, there are several issues is known for Wheeler-DeWitt equation, for example, some operator ordering and so on. And yeah, so what is the point? So if we if we can treat this Wheeler-DeWitt equation very carefully, it can tell us some well-defined answer in two dimension, or yeah, somehow it Wheeler-DeWitt equation works only some special cases, or so what is yeah
Yeah, so I think the Wheeler-DeWitt approach is the fundamental approach. So there must be a Wheeler-DeWitt equation, and there must be a solution, and there must be a semi-classical approximation from the wave function, and so on. This is formally true, I think.
I
However, the question is, can we really solve it? And can we really see beyond such a semi-classical limit? I mean, including non-perturbative effects. That is quite difficult.
see.
Yeah, your point is quite good that if we can do it in simply in two-dimensional case, I mean low-dimensional case, then yeah, this is very worthwhile to investigate. For
Okay,
example, in the
thanks.
two-dimensional case, if you can compute the path integral more exactly, then this will be a very important clue to solve the Wheeler-DeWitt equation. Uh,
I see. Thanks.
yeah, okay, thank you. So yeah, so so today I will focus on the four-dimensional examples, and I will show some way to bypass such an way. So one important exception is that the case that the space-time is homogeneous. So in the spherical symmetric black hole case, the space-time is not homogeneous. Therefore, the potential term has some x derivation or spatial derivation terms. But if you think about the homogeneous space-time, then Wheeler-DeWitt equation can be a partial differential equation because there's no spatial differentials. Then we can solve it. so, so the important example is the cosmological example. I mean, mm, WKB. No. The FRW space-time. So quantum cosmology is possible and because um, uh, the Wheeler-DeWitt equation for cosmological background is the a kind of a partial differential equations. So several days ago, I uploaded this paper in archive, and this shows that this is a one numerical result and this is another numerical result, and this one was about the hot rocking boundary condition, and the right hand side figure is about the Villenkins tunneling boundary condition, but we implemented in the numerical way. So the historical typical approach is to provide the boundary condition in some analytic examples with slow roll, ultra slow roll approximations. But in this paper, we implemented that boundary condition in more generic potentials, and that may go beyond the slow roll limit. But using the computer, you can do it because the computer will solve the partial differential equations. Yeah, so that means at once you have the partial differential equation, then using the computing power, you can solve the equations and you can do something. Uh, Then the question is, how about the black holes? Of course, the spherical symmetric black hole is not homogeneous, so it's not a kind of quantum cosmological examples, but um, this approximation or this description might be possible if we restrict only inside the horizon. Because inside the horizon is equivalent to anisotropy cosmology. So, of course, it's not equivalent to real cosmology, but the metric form is the same as the anisotropy cosmology. So, I mean, inside the black hole can be regarded as a kind of homogeneous space-time. And then, since it's homogeneous, you can write down the Wheeler-DeWitt equation as a partial differential equation. So this is the procedure. So you start from the Schwarzschild black hole metric. It's very well known, Schwarzschild space-time. And what we are interested in is to focus on this black hole interior inside the event horizon. Then the time slicing is spaced like this way. And along this time slicing, it's homogeneous. That's the point. So if you change the variables, then you can present the metric in this way, where x is a function of the time and y is also a function of the time. But you can notice that the metric variables is independent of spatial variable, say capital R, and it only depends on time. So practically, this is something like the anisotropic cosmology. So this is the classical solution inside the Schwarzschild black hole, and you can remove this time, and you can present the relationship between x and y. You can present this way. So this is the relation between x and y, and this is independent of time. This is very important when you analyze the contour in the canonical variable space. So this is the classical contour as a function of x and y. And also you can write down the Wheeler-DeWitt equation. So I will skip every intermediate details, and the result will look like this way. So x is the metric variable of this one, and y is the metric variable of this one. And the potential only depends on y. So you can notice that the Wheeler-DeWitt equation is very simple, and even the separation of variable is possible, and even the analytic solution is possible to obtain. Uh, Already, this decomposition was already known by several people in 1994 and 2001 and so on. So this is not very new, and it's already known that you can present this way. So you can introduce the separation of variable where k square is the separation constant. From now, it's nothing but just the undergraduate quantum mechanics problem of two-dimensional system. So the x part, the solution is exponential, blah blah, and y part is more complicated. But anyway, the Mathematica will solve it in an analytic function. So this is the kind of Bessel function. So I don't know the very mathematical details, but this is the Bessel function of some kind. So so-called Bessel k, and this is Bessel I. So this is the generic solution with the linear superposition, but the same as the usual quantum mechanics problem, one of them doesn't satisfy the boundary condition. That means it diverges in some limit. So in the large y limit, this I function diverges, and therefore it's better to choose this C2 coefficient to be 0. Then the entirely bounded solution should look like this way. So the entire generic wave function should be the multiplication of exponential ikx times Bessel k. And fk is some coefficient of each k. So if you write down this way, then this looks like a kind of wave packet. So of course, in this function of x and y, there's no time or no space, but you can practically interpret that this is a kind of wave packet that moves in the space of x and y, canonical variable space. So previously, as I mentioned several years ago, people already know that Wheeler-DeWitt equation can be written this way in 1994 and 2001. But in these old papers, they specified these eigenstates only, and they stop in that level. But in my opinion, these eigenstates are very difficult to interpret. Indeed, the more important thing is to explain the classical trajectories introduced in the wave packet. So in my paper in several years ago, we interpreted the interior of the black holes using this wave packet by choosing FK. So if you introduce FK, which looks like the Gaussian wave packet, so there's no reason to choose this FK this way. But if you choose this way, then this wave packet coincides with this classical trajectory. This is something like the Ehrenfest theorem. So there is a wave packet, and the wave packet coincides with the classical trajectory, and therefore this is consistent with the classical dynamics. So in several years ago, I myself and with my colleagues, including Joyo here, so we drew this diagram. So this is x-axis and this is y-axis, and this red contour is the classical trajectory. And the wave packet we construct here is very consistent with this dynamics of the classical trajectories. So red curve is the peak of the wave function, and it is the steepest descent, and this steepest descent coincides with the classical trajectory, and therefore it is consistent with the Ehrenfest theorem. Okay. So this result is not so surprising because in this equation there is a potential barrier along the y direction. That means you can intuitively interpret that there is an incoming pulse and there is a potential barrier in large y limit, and it's bounced back to another way. So it's not so anyway. It's not that surprising that there is a bouncing behavior. And so, in x and y plane, this red curve is the classical trajectory where this right part, and that means large x and large negative y region, this corresponds to the singularity, where this another end corresponds to the event horizon. So it's nothing but there's a so this solution is consistent with the classical trajectory, and nothing special happens. Even though you solve the Wheeler equation, the my wave packet is consistent with the classical trajectory, and nothing happens near the singularity. Yeah, it's not too bad, but it's not that good. So I was disappointed because the space descent simply moves toward the singularity, and there's no new effect from quantum gravity. So singularity is not resolved based on the Wheeler approach. So yeah, I was a little bit disappointed, but later I thought that maybe we can think something because there is a quantum bounce here. So as I mentioned, in the large Y limit, there's a potential barrier here. So incoming wave might be bounced to here. So for this left part and right part, it's okay. So it's a very well-defined classical dynamics. But between left and right patching, there is an ambiguity to define the arrow of time. How to introduce the arrow of time, and is there any unique way to assign it? If it's not the case, then you can interpret this way. So this is just the typical interpretation that there is only one arrow of time from horizon to the singularity. Then nothing new happens. However, relying on some ambiguity of the time arrow, if the time arrow moves backward in time here, then you can draw this way. So here's a bouncing point approximately r equals m, and the one time flows from event horizon to r equals m. But in the another part, you can interpret that the time flows in opposite direction. So, of course, this is not a correct Penrose diagram. More correct picture is something like this. So, that means our wave package shows that there is two ways to interpret that wave package. So one is just a traditional classical interpretation, but there is another way that this one wave and another wave are annihilated at r equals m surface. Uh, this annihilation is something like the destructive interference of the potential barrier. So if you think about this way, then it's very interesting. So there are two classical space-time, and they are annihilated at some surface, and wave function disappears. I mean, wave function should vanish at some point. So this is a very opposite process of creation from nothing, and I nicknamed this process the annihilation to nothing. So this annihilation interpretation is allowed inside the black hole. So this may be an opposite process of the creation from nothing. And maybe this is a kind of possible realization of the DeWitt boundary condition. DeWitt boundary condition means that if there exists a singularity, then the wave function near the singularity must vanish. And this is a kind of realization of such a DeWitt boundary condition. So if you accept the DeWitt boundary condition, then can it resolve the information loss paradox, or is it more harmful to understand the information loss paradox? And about that point, I'm not entirely sure. But anyway, so it's important that based on the Wheeler-DeWitt analysis, we can notice that there is a way to assign the DeWitt boundary condition. Yeah, so as I mentioned, there are some ways to indirectly solve the weird equation of the black hole, and one way is to restrict our interest only inside the horizon. However, is there any other way to extend outside the horizon? As I mentioned, it's not easy to solve because the weird equation is ill-defined. However, we can find a solution of the Wheeler-DeWitt equation without solving it. So it's kind of cheating. I mean, it's a kind of cheating the solution of the Wheeler-DeWitt equation. The question is how to do it, and the answer is to rely on the path integral. Because even though you cannot directly solve the Wheeler-DeWitt equation, if you write down the path integral, then it's the formal solution of the Wheeler-DeWitt equation. So if you start from the path integral, then you don't need to solve the Wheeler-DeWitt equation in some sense. So in Hawking's paper in 2005, he mentioned that the only sane way to do quantum gravity non-perturbatively is the Euclidean path integral approach, because path integral itself is not easy to compute, but if you analytically continue to the Euclidean time, and then there is a very nice way to approximate this Euclidean, in this entire path integral. And therefore, you can compute something, and therefore, you can compute some non-perturbative effects. That's the idea. So what's the path integral? Path integral is the propagator from in state to some out state. But in general, there's no unique future boundary, and the final boundary must be the superposition of several classical boundaries. This picture is already written in conceptually written in Hartle and Holt's paper. So this is a very usual behavior. Then initially you start from a single classical boundary, but as time goes on, it branches to multiple histories. That's the usual process. And of course, we have to do the formal path integral from initial to final boundaries, but it's very difficult. I don't know to compute the Euclidean path integral exactly, but there is a good way to approximate this so-called steepest descent approximation, or compute the Euclidean actions based on the using the instantons. Then this will be a good approximation of the entire process, and this allows to compute the probability from initial to some classical boundaries. So we can compute the tunneling probability from I to F1 and I to F2 and I to Fj. This is the idea. And there might be very diverse kind of instances, and in principle, you must include everything. And also it's very difficult to say we include every instanton contributions, but yeah. So indeed, really, there are many kinds of instantons, including free scalar field instantons. So in this paper, with Professor Pissen-Chen and Professor Misao Sasaki and me, we noted that free scalar field instantons can cover the Hawking radiation if their amount is sufficiently small. If the contribution is very small, then indeed scalar field instantons are a kind of Hawking radiation. So Hawking radiation is indeed this kind of instantons. We interpret it this way. However, if the amplitude of the scalar field instanton increases, then the contributions are no more perturbative, and indeed, this must be non-perturbative contributions. So if this delta m, so I mean, instantons will carry out the energy, and if delta m is the same as capital M, the original black hole mass, then due to this instanton, black hole must disappear because the instanton will carry the entire energy and the black hole will disappear. And of course, then topology is changed and information must be recovered through these instantons. So one can, what we have shown in this paper is that always there must exist such a process. Then what is the price of this kind of topology change? And the price is the probability. So, if you carry out every mass using these scalar field instantons, then the probability is exponentially suppressed. The exponential minus m square is the typical probability. So you can ask, can we really explain the phase curve using this Euclidean path integral approach? And I cannot say details because of the time limitation of today. I spent almost all time, so I should quit my talk. But the detailed computations are in this paper, and it seems possible. So the point is that uh, so one can mimic a phase curve. The basic idea is if you have the black hole, then in the most conservative descriptions, then entanglement entropy should monotonically increases. Then if it monotonically increases, then this cannot explain the unitary evolution. However, if the black hole spacetime tunnels to the topologically trivial spacetime, then black hole disappears. And there's no singularity, no event horizon, and therefore the entanglement entropy must go to zero because there's no interior at all. So there must be two competitive contributions of the entanglement entropy. One is the typical semi-classical space-time with horizon and black holes, and through this contribution, entanglement entropy must monotonically increase. However, there is S2. That means after the topology change, black hole disappears and the entanglement entropy should drop to zero. Then what is P1 and P2? Because P1 is the probability to stay in the semi-classical history, and P2 is the probability to transit to the new trivial topology. And probably P1 and P2, P1 plus P2 must be unity. And then after some careful computations, what we notice is that P2 must be dominated in the late time. In the early time, P1 is dominated exponentially. Therefore, P2 is negligible. That is the semi-classical behaviors. But in the late time, the space-time must transit to the trivial geometry. So P2 must be dominated, and therefore, initially the page curve is more or less monotonically increases, but in the late time, near the final stage, this must drop and must vanish eventually. Therefore, at the end point, entanglement entropy vanishes and information is recovered, and this explains the unitary evolution of the black hole evaporation. But some people will think this is uncomfortable because this triangle is the usual page curve. But my curve is far outside this typical page curve. That means that at some moment over here, the entropy boundary relation must be violated. That means the Boltzmann entropy must be greater than the aerial entropy or Bekenstein-Hawking entropy. Then is it acceptable or not? And we must answer about that later. So, okay, so this is my almost the last slide. So up to now, I studied non-perturbative effects of evaporating black holes. But the point is, I could not directly solve it because it is ill-defined. So the way to bypass, the way to solve without solving is that either we focus on the inside the horizon only, or see the outside using path integral. Then you can bypass the difficult to solve the Wheeler-DeWitt equation directly, and method 1 and method 2 both from these approaches, we may learn a lot from these studies, especially non-perturbative effects and quite interesting and funny behaviors here and there. However, frankly speaking, I think it's not perfectly satisfactory to me. Um, so how about to choose the time slice that covers outside and inside together? Then the Wheeler-DeWitt equation is really not possible to solve it, and also the path integral, Euclidean path integral, is not very defined for the slicing. Then can we really solve the Wheeler-DeWitt equation, and how can we understand the Wheeler-DeWitt equation and its a solution, wave packet, and so on? And so still, I don't know the correct answer, but there might be some indirect ways to digest such a process. Let's find wisdom to solve the equation for evaporating black holes more directly. That covers both inside and outside the horizon. This may be a very interesting future research topic. Okay, that's all. Thank you for listening.
Thank you very much, Jonathan, for this nice talk. Are there any questions?
Johan, let me ask one first, maybe.
Yes.
So in the annihilation to nothing part, so the annihilation appears at when the black at the radius that the black hole is roughly the mass of the black hole, which is somewhere between
Right.
in the halfway between singularity and event horizon. So of course at that moment we struggled a bit about this, why this is the case. But I do you think that this can be related to the fact that in the usual triangular shape of page curve, the peak of the page curve is also at the middle? And I mean the page time is also at the middle, like when the evaporation process is still in the halfway. Do you think there's a way to relate it to relate these two notions? Or some
At this
people have
moment,
already
I
done
have
this?
no idea. At this moment, I have no idea because uh, this is the interior of the black hole, and practically there's no time dependency here, but the
Right.
phase curve includes some time dependence. This is a different, I mean, separate question. But maybe there is some way to relate. I mean, after some time, the probability should drop, and maybe this Dewey boundary condition may help to drop the probability. No, I mean drop the page cover in the earlier time. However, at this moment, I have no direct way to relate these two ideas, but it's an interesting question.
And another question about like the path integral approach. So you showed that once you have P1 and P2, these two different contributions, you can have a like school-like page curve. So I'm curious about what those different colors represent.
I see, I
So
see.
what controls the peak of the curve?
So, different colors means the different initial condition. So, if
Oh,
you start from a smaller black hole, then maybe looks like a black. But if you think about very large black hole, then it will follow this red curve. So
I
it
see.
depends on the initial starting mass of the black hole.
And do you think that if you include more contributions from like different results of path integrals like P3, P4, and so on, do you think that the results would still remain the same or would be quite different or not?
Of course, it must be modified, and maybe such a decreasing behavior must be uh, in the earlier time. If you think about more multiple channels, but if you, but I'm not sure whether this curve will be drastically changed. I mean,
Oh,
this red curve will be changed to this triangle, but I'm very, I don't think that really happen because the probability hierarchy is more or less exponential. So anyway, it's interesting to include multiple stories and their contributions to the entanglement entropy, and then how can it be changed, and will it be drastically changed or not? So it's still open to me.
I'm just
I'm not
curious
sure.
whether by adding more channels, whether you can bring the school-like shapes back to the triangular shape.
Yes. So I don't believe that it will be such a drastically changed,
Ah,
but it must be changed a little bit, right?
okay. Thank you.
We have a question in the chat. Shall I simply read it to you, or do you want to read it yourself?
I'm sorry?
Shall I simply read the question to you, or would you like to read it yourself? Maybe I just read it. Thank you very much for the nice talk. A follow-up question. For the annihilation to nothing process, can you elaborate a bit more about the universe state transition? Exactly to what state it is annihilated to?
You mean, is there any analogous cosmological example of annihilation to nothing? Is it your question?
But I think it's more about like, yeah. Okay.
Oh, okay. Yeah, it's interesting. And in the cosmological case, okay. I don't know. I didn't think about that, but it's an interesting question. And what's the then if it happens, then what's the cosmological implications? Yeah, I have no idea. Yeah, right.
Thank you from the chat. Are there any other questions? Maybe I have a question which is a bit bordering the topic. Do you think we can learn something from combining in a very careful way observations and theory? May this help us to understand more about how we should approach quantum gravity? I mean, right now, from my understanding, we approach quantum gravity a bit in the direction that we try to transfer what we learned from quantum mechanics to gravity. But of course, we don't really know if that's really the case or not.
Right. So yeah, I don't know. So this is the correct answer to your question, but I think we can. So of course it's not easy, but we can do some computations that can be demonstrated by experiments. For example, several days later we will report some result that from some quantum cosmological scenarios. So universes are created, and based on such a scenario, as a consequence of that scenario, this will say some expectation about the CMB data. And it's a kind of a power spectrum, and the power spectrum shape must be a little bit tilted. Um, so not equivalent to the Ponce-Davis state. If it happens, then we can expect some expectations, and maybe some future uh, observations will confirm or disprove our assertions. So in that sense, still we have some hope to compare with the experiments, but it's also it's fair to say that it's very challenging. I don't know whether it's a good answer to your question or not.
I think right now it's one of the few answers you can give in this direction. Thank you very much. Are there other questions? If not, maybe we can close the official part of the seminar. Oh, there's another follow-up question which just appeared in the chat. Another follow-up question regarding the page curve and non-trivial tunneling to flat geometry. In island conjecture, it is argued that after page time through replica trick, the black hole is classicalized. Is it possible to apply similar trick to a Euclidean path integral?
Okay. Yeah, right. So, according to island conjecture, after the page time, some replica wormhole contribution is dominated. So I think there is some, I mean, Euclidean path integral approach is not the same as this replica or island computations, but there are some common ideas. That means before and after the page time, so the dominant contributions are different. So in the island conjecture, before the page time, some contribution is dominated. After the page time, another contribution is dominated. We are the same. So, I mean, Euclidean passive integral approach seems to say the same, same idea. However, the technical details are quite different. So that's the reason why the page curve shape is quite different. So, um, in the Euclidean passive integral, can we apply the same trick? I mean, replica trick, and then I don't know. But the point is, replica trick is about the density matrix, but Euclidean passive integral is about the quantum state. So I think the quantum state is more fundamental than the replica computations. So in that sense, in my opinion, in my private opinion, Euclidean passive integral is more fundamental approach. But yeah, it might be criticized.
Thank you from the chat. Are there other questions? If not, I would say we close now the official part. Jay, could you stop the recording?